Hello and welcome to this video lecture. In this lecture, we will continue our discussion continue with our review, or part one of our review of linear algebra. And we're going to do that by continuing the discussion by bringing vectors into the picture. So I want to make a note, though, of course, at this point, that we will be discussing this idea of vectors here. We will, of course, though, be formalizing our understanding of vectors a bit later in the class, specifically when we start talking about the second part of the linear algebra review. So here I'll say, even though we will define vectors more formally later, for now, we're just going to say that a vector is a list of numbers. So rather than being an array of numbers, and I guess you could consider a list an array, just a subset of arrays where we just have numbers listed out in a particular sequence. A vector will have n values, otherwise known again as entries. And so that means that when we have a vector, in order to uniquely identify which number we're discussing or which number we are interested in, we can say that each number can be uniquely identified by its location I in the list. And so we can see then that this idea of a vector is slightly different than the idea of a matrix, where a matrix is this two-dimensional array of numbers. We can now see that this vector is a subset of matrices where it's just a one-dimensional array. So bringing in this idea of dimension, though, we can say that the dimension of a matrix let's go ahead and move that over a little bit more. So the dimension of a matrix refers to the number of values required to uniquely identify the location of any and all particular entries. So we can see that that two-dimensional matrix that we were talking about before, where we had rows and columns, that took two values, namely I and j, to identify any particular value in that matrix, and of course, provided that we didn't skip any values from 1 to n for I or 1 to m for j, then we could of course capture all the values. We could uniquely identify all the values associated with that particular matrix. So since we needed two values, two quantities, it's a two-dimensional matrix. On the other hand, this idea of a vector, where we're assuming that all we have is just a single list of numbers, that vector would only take a single quantity, in this case I, to identify which entry we're interested in that list. So clearly that means that a vector is a one-dimensional entity. So let's go ahead and get that down. So since matrices require two values, I and j, as I indicated before, to locate an entry, that means that, of course, they are two-dimensional. Entities. And as I also indicated, clearly, since vectors require one value, in this case just I alone, to locate an entity or an entry. Yeah, sorry, should say entry. Then clearly they are one-dimensional. Entities. And so, as I already kind of spoiled, clearly this then means that vectors can be viewed as a subset of two-dimensional matrices. Here I'll just say 2D matrices. Which of course are those two-dimensional matrices, or those matrices. So I shouldn't say two-dimensional. Let's just say those matrices that have only one dimension. In other words, those matrices with either I or j equal to 1. The key here, though, is but not both. And here I should qualify where I or j equals 1 for all entries in the matrix. So that says then that when we are looking at vectors, we're looking at essentially a, if you want to think of it this way, a simplified form of a matrix, or in another, in a more mathematical way of saying it, we're looking at a degenerate matrix. Now we can ask ourselves though, because why did I have to restrict with this last statement, but not both? I and j being equal to 1. Because if both are equal to 1, what does that mean then? That means we're dealing with an entity where we only have a single value. And at that point, we just have one entry. And there is no need to use any kind of addressing, whether it be I or I for vectors or I and j for matrices. When both of those are equal to 1, there's no need for any kind of addressing associated with that entry. We just have to name this quote unquote matrix, and then we immediately know that we're talking about that one entry, and that's it. We've uniquely captured that one entry just by naming the matrix. And so of course, what does that mean? That means we need no values, no quantities to uniquely locate that particular value in the matrix, because it is the matrix. And so of course, if both I and j are equal to 1, we're then dealing with a 0-dimensional matrix. And if you think about it, that just means that we're dealing with a single quantity. Well, what's a single quantity? That is essentially dealing with a scalar. Though, of course, if we're looking at a scalar as a particular type of matrix, we would have to make sure that everything that we're dealing with from a scalar perspective makes sense with considering it in the context of being a matrix. So we have to be a little bit careful there. So anyway, but we can see that sure enough, if we have a one entry matrix, that's it. It has 0 dimension associated with it. So with that said, since we can see that vectors are nothing more than a specific class of matrices, and as we discussed before, matrices are the properties of matrices are dependent not only on the values of the quantities that make up that matrix, but also their position in that matrix, that also has to hold true for, of course, these vectors. So going ahead then and capturing that, just want to try to get my indentation roughly correct here. So I'll just eyeball it in there, okay, because that was a little bit of a discussion. And so, of course, this means that the properties of the vector will be determined of course by the values in the collection, or the set if you prefer, and the key here, of course, is the and their location. In the arrangement. So since we have a single list of numbers, it turns out that there are a couple ways in this context of matrices, there are a couple ways we can represent those lists. Let's go ahead and look at both of those ways. So a list of numbers arranged in a row is, of course, called a row vector. Not EQEG. Now, I know in the past you may have used an arrow to denote a vector. Here I am going to adopt the underline notation to denote a vector. So this vector V, this row vector V, is simply going to be comprised of values V1, V2, all the way on out to Vn. And since they are written horizontally, i.e. in a row, this is, of course, going to be a row vector. So an example, of course, for a row vector would be that V is equal to, using my favorite set of numbers, 1, 2, 3, and 4. And there we go. We have a 4-entry row vector, a one-dimensional entity. Okay, so clearly, if we can arrange numbers along a horizontal line and call it a row, we can also arrange the entries along a vertical line, in which case then the column, the vector will be a column vector. So a column vector if the list is presented as a column. Now, of course, when we look at what's going on with column vectors and row vectors, this may seem to be a relatively trivial distinction, but when we go back and start looking at the matrix multiplication operations that we've already identified, specifically, well, the one matrix multiplication operation that we've identified so far in this class, clearly it would be important whether I'm dealing with a 1 by n matrix or an n by 1 matrix. So please understand that it is crucial for us when we get to a formal representation of what's going on with matrix multiplication to understand what kind of vector we're dealing with and make sure that we are using the proper vector in the proper location for a particular mathematical matrix mathematical expression. So it does become important for those particular cases. And of course, we really couldn't add a row vector to a column vector. There would be essentially no way to do that. So again, to write out a column vector a little bit generically, we would generally write it as v1, v2, all the way on out to vn. So now that we have an understanding of this concept called a vector, or this arrangement and a concept called a vector, let's go ahead and start talking about mathematical operations associated with this particular type of entity. So vector addition and scalar multiplication Oops, sorry, ran out of room there. I'll move over a little bit, give myself an N, and then immediately move everything back. So as you can imagine, those two, since they were very similar to their scalar or algebraic analogs, we have the same addition and scalar multiplication for vectors as we had for matrices, and nearly essentially what we had for algebraic expressions as well. So with that, I'll just briefly run through vector addition. And just like we did with matrices, we add corresponding elements of the vectors involved in the addition operation. So if we had v1 plus v2, and here I'll just use some numbers, 1, 2, plus, so that'll be vector 1, vector 2, shockingly will be 3, 4. And of course, when we add 1 to 3, we get a 4. And when we add 2 to 4, we get a 6. And that would be the new vector. Here, I'll just go ahead and call that vector v3. So here, this will be equal to v1. And here, this will be equal to v2. So just as we saw before, but it's worth noting it again. Well, I should say just as we saw before with matrices, but it is worth noting again that v1 and v2 must be the same size. Here, I'll just kind of, since these are notes, I'll just kind of keep going down with these colons. Clearly, we can see that the result, and not surprising, but nonetheless, it's worth noting, the result of this operation is another vector. And of course, you can see from the definition that there would be no other way to, or no other entity that could be formed by that kind of operation by definition. But nonetheless, it's good to note, yeah, we add two vectors together, we're going to get another vector. And as we can see, because the order of addition when it comes to the individual corresponding entries of a matrix, that order of addition doesn't matter, then the order of vector addition also does not matter. Additionally, we can quickly capture, so that captures vector addition, we can quickly capture scalar multiplication. And here, again, it is no different than what we had for matrices. So we just go ahead and multiply all the vector elements or entries if you prefer by the same scalar. So if our scalar is alpha and we multiply v1 by alpha, let's say that alpha is 3 because v1 already took 1 and 2, since I'm going to use the same v1 as before. And so we can see then that we take 3, multiply it by 1 to get 3 as the first entry of our new vector, and 3 times 2 gives us 6 for the second entry. And we'll just go ahead and call that new vector v2. And so clearly you can see with what I've done here, each of the entries of v2 is or can be mapped to an entry in v1 where that mapping is just multiplying by this value alpha, which is 3. So clearly we can see that the result of this operation assuming we're starting with a vector, of course, is simply just another vector. Again, not at all shocking, but still good for us to make a note of that particular property. And since it doesn't matter whether I multiply 1 by 3 or 3 by 1, same thing with 2 and 3, I can multiply 3 by 2 or 2 by 3. It doesn't matter the order in which we write the quantities associated with, or the entities associated with this scalar multiplication. So we can have alpha times v1 or v1 times alpha. So alpha, again, can be viewed as a zero-dimensional entity, if we like. So that covered the most straightforward extensions of mathematical operations from that we would normally see in algebra to now our vector mathematics here. But clearly, since vectors are a different type of entity than scalars were in algebra, scalar quantities were in algebra, we can then start to envision types of operations that have no direct analog in algebraic math. So with that said, let's go ahead and look at vector multiplication. So vector multiplication, as I just indicated, is somewhat different than algebraic multiplication, but it turns out that it is also possibly different than matrix multiplication. And let's see how that can be. So to introduce that, I will say that there are two common approaches to multiplying vectors. And I'm sure you're familiar with these two most common approaches. Let's go ahead and start with the one that almost all classes start with. So I don't want to deviate from that, which is, of course, the dot product. So the dot product itself results in the sum of the products of the corresponding elements in the two vectors, or that make up the two vectors. Here, I'll just go with n for simplicity, where those two vectors are v1 and v2. And the dot product itself is written as v1 dotted into v2. Well, that's kind of an interesting statement. So if I have v1 dotted into v2 and v1 is equal to v1 comma 1, v2 comma 1, where the first subscript represents the entry in the first vector and the second subscript represents the vector that is an entry of. And so then we can go all the way on out to vn comma 1, and we're going to say that that is dotted then into v1 comma 2, because now we're starting to talk about the second vector v2 comma 2 all the way on out to vn comma 2. And we can see that this dot product is equal to v1 comma 1 times, here not a dot, just times, v1 comma 2 plus v2 comma 1 times v2 comma 2 plus dot 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 plus vn comma 1 times vn comma 2. And that captures the value of the dot product. Now, the reason I was saying that this is very interesting is because if we think about it, and if we choose to, and we'll do this, and I'll mention it, in the class at the appropriate times, if we choose to look at matrices as collections of row vectors and or column vectors, what can we see? We can see that when we were looking at matrix multiplication for a particular entry in the resulting in the matrix that results from that matrix multiplication operation, we were just looking at the results of a bunch of different dot products, where we were dotting the rows of the first matrix or row vectors of the first matrix, dotting those into the column vectors of the second matrix. And that's all we were doing. So if you want to think about what was going on with matrix multiplication and then kind of come over here and look at what's going on with vector multiplication, even though we are looking at this in a, through a separate lens, the lens of vectors, we can see that the same mathematical patterns existed when we were talking about matrix multiplication, as now exists when we're talking about this dot product associated with vector multiplication. One thing I do want to note, and I know I said it, but I always like to kind of get it down. So that way, when you're reviewing your notes, this, of course, is V1, and this, of course, is V2. So just like we have with our other mathematical operations, let's look at some of the properties. So notes, V1 and V2 clearly must be the same size. Additionally, the result, and of course, for that first note, that's clear from the definition itself. We have to have corresponding entries to multiply together. If we don't, then we have an invalid operation. The result of the operation is a scalar. And that's pretty obvious, again, from the definition, because we're multiplying scalar quantities, or I don't want to say, okay, let's go ahead and say scalar quantities. We're multiplying scalar quantities together and then multiplying those products, or adding those products together. Of course, we're going to just end up with one value. So we're going to end up with a scalar. And as we can see, since the order of multiplication, just as long as we properly multiply the corresponding entries together, the order of that multiplication is irrelevant. And of course, the order of addition doesn't really matter, though it wouldn't change whether the addition order wouldn't change whether we reverse the order of the vectors in the dot product. We can see that V1 dotted into V2 is the same as V2 dotted into V1. And so then we can see that, well, actually, before we go on to the next thing that we can see, let's look at, I don't want to do an IE, let's do an example. And then we'll go ahead and tie this or connect this to other things that are pertinent to what we have or will be discussing in the class. So going ahead and dotting V1 into V2, and it should be little surprise that V1 is going to be 1, 2, and V2, then you guys are probably already filling it in, will be 3, 4. And so then what do we get? Well, clearly we get 1 times 3, because those are the corresponding terms in vector 1 and vector 2. So 1 times 3, and then we add this to the product of the second entries, 2 times 4. And of course, what do we get? We get 8 plus 3, and we can see pretty quickly that we get a value of 11, which, as expected, the inputs going into this operation are vectors, the output is a scalar. Okay, so now let's bring in some broader context. So the dot product is an example of what's called an inner product. And what do I mean by an inner product? Well, this is an operation. So an inner product is an operation nice if I got the right number of p's in there, though. That combines two higher dimension entities and these entities could be things beyond even matrices. So understand that in vectors and matrices. So understand that here we're starting to touch on concepts that even go a bit outside of linear algebra. So an operation that combines two higher dimension entities and produces a lower dimension entity. And of course, what am I saying here? We take two one-dimensional, here I'll just do 1D because we have vectors. Those vectors are 1D, two one-dimensional vectors. And this operation will produce. So two one-dimensional vectors produce a zero-dimensional scalar. In the case of this definition of the dot product. So that gives you an example of an inner product. Now, you might be thinking, oh, why would we ever want to do that? Let's not use a little arrow there. So let's note that clearly, and as you're looking at this potentially, higher dimensional entities convey more information, and that is true. And lower dimension entities equal less info. So you might think, why would we less information? So why would we ever be interested in using an inner product? Well, let's go to a different example where sometimes being swamped by a lot of information isn't actually helpful. If we have some kind of data set and we're looking at all these varied numbers, all these varied values, and generally pairs of values associated with that data set, we may not be able to make sense of what's going on, or we may not gain as much insight as to what's going on than if we potentially take one of those sets of numbers, maybe for the value that was measured, potentially measured over time. And instead of looking at all those individual values, we look at the mean value. And have you ever done that before as engineers? Absolutely, I can guarantee you have. And I can also guarantee that by looking at that data set through the lens of a mean value, that started to give you a lot more insight into what was actually happening than just looking at all these crazy data points. So you can see there, what did you do? You took all of that data and you distilled it down to one number, and you found that one number more useful than all the numbers that you originally had. Or you found the calculation of that value added much more information and much more, well, let's say it this way, much more insight into what was going on with that data set than just dealing with the data by itself, because the data is still there. I don't want to exclude that. At least for you, the data is still there. And so the mean value was a tool in addition to, or a tool that gave you insight in addition to the original data that was used to find that mean value. Now, of course, as I said, you have access to the data. Now, if you just go and write a report and report out that mean value, then, and you don't provide anybody the data associated with that mean value, now all you have is the summary information, and that may be adequate, or you might be missing things. But understand, sometimes being able to simplify things and look at summary quantities, especially summary quantities that are helping us identify some very particular aspect of whatever situation we're looking at, can be incredibly valuable. So less info, but specific summary information, and summary information that has, in some cases, very important physical significance, at least for us. That's why we're interested in it as engineers. So that gives us an understanding of what's going on with our first vector multiplication operation. Now, I'm going to go off on a little bit of an aside here, because I want to bring things in a little bit more, or bring in, let's say it this way, bring in other aspects of the discussion into this particular, or bring in other aspects to this particular discussion. Ooh, boy, wish I could talk right now. And so let's go ahead and define another operation. Let's go, but it is not a multiplication operation. This is a unique operation to matrices. Well, I wouldn't say unique, but certainly has no analog in algebra. Just kind of trying to keep my eyeballs on that one there as I scroll off, because I want to introduce what is called the transpose. So if we define an operation I guess I don't need that comma. We'll just do called the transpose. And this operation produces a new matrix B And of course, since you already know about the transpose, here we're using the columns of A as the rows of B. And that's what we will call the transpose. So if we have a matrix A, let's go ahead and give ourselves an equal sign. And we have A11, A12, all the way on out to A1M, and we have A21, A22, all the way on out to A2M, and we go all the way down to AN1, all the way down to AN2, and then all the way on down to ANM. And we'll do 3 dots all around. Then when we look at taking the transpose of this particular matrix A, and of course that will be matrix B, will be A transpose. And so you can see, let's use lowercase t. My apologies. A transpose. We can then see that B is simply going to be A11, A22, because of course the diagonal elements don't change, but to turn this row into a column, we would have A12 here instead of A21. And then we would have A13, etc., all the way down to A1M here. And then, of course, we would have A21, and then we would go all the way down to A2M, and then we would go all the way across to AN1, all the way across to AN2, and then all the way through to ANM. And that would be the transpose. So we can see that the transpose is clearly going to impact the off diagonal terms. And we're just going to take the entries that were in the upper triangular region above the diagonal, and they'll now become, with the transpose operation, they'll become the entries in the lower triangular area. And so, or the below diagonal entries. And of course, the entries that were originally below the diagonal will switch up to entries that are above the diagonal. And so there you have what is going on with the transpose. Now, here I'm kind of talking a little bit using square matrix terminology. Of course, in this particular case, we may not have a square matrix, but you can kind of see what's going on. The diagonal terms will effectively remain the same, and then we'll just be swapping other terms around, those diagonal terms. So with that, let's go ahead and use an example. And as I indicated or kind of spoiled for you, let's go ahead and make it a square matrix. And so we'll have matrix A, my favorite matrix, 1, 2, 3, and 4. And so, of course, then B is equal to A transpose is equal to 1 and 4 don't change their locations, but 3 and 2 clearly do. And there we go. So we go from a row of 1, 2 to now a column of 1, 2. We go from a row of an A of 3, 4 to a column in B that is 3, 4. And there we go. We have our transpose. So now, as I indicated before, we can then bring together that idea of, and so now, because I know I talked through it before, but now let's go ahead and get it in your notes. We can tie together the idea of the dot product and matrix multiplication. Then the dot product can be expressed equally well via matrix multiplication. So assuming 2 row vectors, we can then, so let's get that down, assuming V1 and V2 are row vectors, then we can see that instead of writing V1 dotted into V2, we can say V1 times V2 transpose, where this multiplication is matrix multiplication. We have V1 comma 1, V1 comma, or sorry, 2 comma 1, V2 comma 1, all the way on out to Vn comma 1. And then all of that multiplying V1 comma 2, V2 comma 2, all the way down to Vn comma 2. And we can make a note here in a moment, but I want to finish this up. And then we have matrix multiplication, where we just multiply the elements in the row of V1 with the elements in the column of V2 transpose, and we add all those products together. So, because remember, that was the definition of matrix multiplication. So we get V1 comma 1 right here multiplied by V1, and here I'm not going to write the dot for multiplication, V1 comma 2 plus, then we have V2 comma 1 times V2 comma, no, not dot, V2 comma 2 plus, and then all the way on out to Vn comma 1 times Vn comma 2. And if you notice, this is exactly the same. So this is exactly the same expression as V1 dotted into V2. So we've now tied this idea of the dot product being the same as a specific type of matrix multiplication. So the two give us the same effect. And we can then say tying this to the idea of matrix multiplication overall. And I shouldn't say that the two give us the same effect. The effect is the dot product. So let me kind of rephrase that. The effect is the dot product. This result is the dot product as I described the dot product before. These are just two different ways of representing the dot product using different types of notation. So that's probably a better framework to put it in, is that they are both dot product, just we're representing that dot product in different ways. Okay, so now, as I did before, we're ready to bring in the idea of matrix multiplication. So we can say that, therefore, matrix multiplication so I didn't make that connection before between the dot product and the dot product of the vectors and matrix multiplication of the vectors done in the appropriate way. So now you can actually see that this connection is even a little bit more nuanced than I might have indicated before, and you might have thought before. So therefore, matrix multiplication can be viewed as the dot product of all the row vectors in the first matrix. There we go. I finally got my tongue untied. With let's get all. I really want the all in there. With all of the column vectors of the second, or making up the second matrix. Okay, so we can tie the dot product to a vector notation that is its own unique notation for that particular operation, i.e. using the dot itself, or we can tie it to notation that we're already familiar with matrix multiplication, but then we can broaden it out to this idea of multiplying two matrices together rather than two vectors together, but then looking at the matrices as collections of vectors. So you can see how all of these different ideas are all running around this particular vector multiplication operation. So it's very interesting, very rich, all these connections that you can make. And personally, I think it's a lot of fun. So let's go ahead and talk about an interpretation of the dot product. So let's say for right now, because it's relatively easy for us to visualize it, if the two vectors, here, let me spell out two because I don't want too many numbers running around. So if the two vectors are in 3 space, in other words, 3-dimensional space, because that helps us visualize it, then those two vectors will create a plane. That C kind of looks a little halfway between a C and an E. Sorry about that. So those two vectors will create a plane. The value then of the dot product, let me get a space, a little bit of a better space in there. So the value of the dot product is simply the norm or the magnitude otherwise also known as the length of one vector multiplied by that of the other vector, so by the length of the other vector, times the cosine of what is called the included angle, which is the angle between those two vectors, the included angle. Between those vectors, here I'll just consolidate that into them, in that plane. So then we can see that taking that description and turning it into much more compact, much more efficient mathematical notation, we have V1 dotted into V2 is equal to the magnitude of V1, which we'll just represent as V1 without the vector notation, times the magnitude of V2, which again, we'll just have the vector notation stripped away from it, indicating it's its magnitude, times cosine of the included angle theta. Where, of course, the magnitude, specifically for V1, is equal to V1 x squared plus V1 y squared plus V1 z squared. Since we're dealing with 3 space, we can just assume we're dealing with a rectangular system. And of course, and this is the magnitude of v1, the vector, v2 is essentially the same thing, but now just for vector 2, v2x squared plus v2y squared plus v2z squared. And this is simply the magnitude of v2. And and since these are wheres, I'll just kind of continue with my colon notation there, just like I have before, using it somewhat like a bullet. And then theta is the included angle, namely the acute angle between the two vectors in the plane created by those two vectors. So in other words, if you're familiar with drafting, it would be the acute true angle between those two vectors. But here, I'll just mention that this is in the plane of the vectors. Now, one of the things that you're probably seeing right here, though, is you're looking at v1 times cosine, because we could group these differently, right? So we could take v1 and combine that with the cosine theta and then multiply that by v2. Or we could group together v2 and cosine theta, multiply that by v1. All of those would give me exactly the same value. But when I start looking at multiplying magnitudes of vectors by the cosine of the angle between those vectors, then I'm starting to talk about the projection of one vector on another. So let's capture then that since a magnitude, and here I'll just shorten magnitude to mag, times cosine of theta is equal to the projection or let's say is equal to the projected length. I'll just write it down. Projected length of one vector on the other vector. That means that we can also write, here I'll just get rid of the we, and I'll just say can, got a little close there. We can also write that v1 dotted with v2 is equal to v1 magnitude times the projection of v2 onto v1, which is also equal to v2 times the projection of v1 onto v2. And of course, this becomes very useful if we just want to figure out what the component of a vector is, because then we can select one of the two vectors to be a unit vector. And then we can start using this to figure out what the components of a particular vector are in a particular coordinate or a specific coordinate system described by or captured by those unit vectors. So we can see how rich this idea of the dot product is. It's an incredibly interesting mathematical operation that has lots of connections. Even though we won't spend quite as much time right now working with the next vector multiplication operation, for a lack of a better word, it turns out that this particular operation is one that we will see again let's say it this way, time and again in this class. So even though we're going to spend a little less time discussing it now, I think we're going to see its properties, our understanding of its properties, and the interpretation of this particular vector operation evolve over time as you work through this class, or as you go through this class. Hopefully going through it doesn't work, but I know it is. And that, of course, is, and let me make sure I'm trying to get my indentations right. It looks like we're pretty good there, so I'm just going to stick with that. So right about here, we'll do 2. And that, of course, is the idea of the cross product. And so what is the cross product? Well, much like the dot product, I'm just going to define the end result, and then we can talk about notation that gets us to that end result. Right now, we're just going to keep the discussion pretty straightforward. So the cross product results in the sum of specific products of the elements from 2 vectors. Again, we'll have those vectors be v1 and v2. Involved, of course, in the operation. This, of course, will be written as v1 crossed into v2. Now, I want to make a note where, so this is kind of a continuation, where the sense of the terms in the sum is assigned using a certain pattern. And let me go ahead and move that and a little bit further out. Because I want it to be at the same level as this too. And a particular unit vector is associated with each term. Now for us, we'll just go ahead and give the end item result. Of course, there are ways of looking at and understanding where all of this is coming from. But for us, I want an IE, not an EG. But for us, we're going to say that this is our cross product. So V3 is the vector that results from the cross product. So note, as I will have soon, that the result of a cross product is a vector. And we have V1 crossed into V2. And here I'm just going to continue with the assumption that we're dealing with vectors in 3 space just to make life a little bit easier for us. And so that particular pattern of multiplying specific elements of the 2 vectors together and then adding them, we have V1 y times V2z, where 1 is vector 1, 2 is vector 2, y is the y component of vector 1, z is the z component of vector 2. I'm not going to go through that for each and every product, but you get the idea. So the pattern, that pattern just continues. Now we add on V1z times V2y, but remember I say that there's a sense component up here, all right? There's a sense associated with that. The sense of the first term is positive, the sense of the second term is negative, and then we associate a unit vector with that particular term simply by scaling that unit vector by the result of that sum with the properly assigned senses. Plus, for our next component, we have V1z times V2x minus V1x times V2z, all that times j hat, plus, and then last but not least, V1x, V2y minus V1y times V2x, and all that multiplied by k hat. Now there are, as I indicated, a number of different ways of remembering that order for those of us that don't have photographic memory, which is probably most of us. So let me give you a way you can remember that relatively easily. So this can be remembered as, and I know again there are variety of different ways of remembering this, but this is the one I find most convenient, where you just write out I hat, j hat, k hat. Let's leave off on the next 2 columns. Then we have V1x, which is, of course, where V1 is the first, and that is an important thing to note, the first vector in the cross product. And we have V2x. Let me write x there a little better. V2y and V2z. And then you go ahead and just rewrite the first 2 columns at the end here. I hat V1x, V2x, j hat V1y, and V2y. And then you capture, so if we distributed out the unit vectors in the expression above, if you go ahead and just draw diagonals across, here I'm doing it in red, of course. And here's the one thing that you have to remember, and it's pretty easy for me to remember because I don't like leading negative signs. So of course, what does this product give me? It gives me my first 3 terms being negative, which always irritates me. So anyway, good irritation, because then I never forget. So then going through and multiplying all this together, we get negative v1y v2x times k hat minus v1z times v2y I hat minus v1x v2z j hat plus, and here I'll just go ahead and do the plus down here, do a wraparound plus. So here plus v1y v2z I hat plus v, and there we are, v1z times v2x j hat plus, last but not least, v1x times v2y k hat. And let's check a couple of these. So let's check I hat first. So we got a v1y times v2z, v1y, v2z, positive, and of course multiplied by I hat. We have a negative v1z, v2y, negative v1z, v2y, also times I hat. So yep, everything checks out. Let's just grab one random one, just this last one here. v1x, and it's the positive one, positive v1x times v2y, yep, and all that multiplied by k hat. So if you go through and provided I made no mistakes, this should be the same as above, just in distributed form. Rather than in that more compact form. Okay, so with that, let's go ahead and ask we have with any of the operations that we have newly introduced. Let's go ahead and write down some notes. So V1 and V2 clearly must be the same size. Now here I'll make a note. Specifically, in 3 space, because, well, let's say it this way. The reason I mention this is because if I have a particular coordinate system and it turns out that one of my vectors lies in the plane that is created by 2 of the unit vectors. In other words, it doesn't have a component in the direction of the 3rd unit vector. It is customary to omit that. And so when we put together, and that is especially true and a little bit confusing when we have no component in what we would consider the 3rd in the direction of the 3rd unit vector. Because then we might be tempted to just write the first 2 components and completely omit the last component, which would then make it look like that vector is in 2 space rather than 3 space. So when we're looking at any of these operations that we're discussing for the vector operations, we need to be careful to make sure that when I say that these vectors need to be the same size, that we haven't inadvertently reduced the number of dimensions that vector seems to be associated with. And here I'm talking, space dimensions, not entity dimensions. Inadvertently made it look like it is associated with a lower dimensional space than it truly is by just eliminating that, generally that last 0 component. And if we do that, that's okay, as long as we recognize it, we catch it, and then we reintroduce that zero component, in which case then we will have vectors of the same size. Okay, so that's a little note here that I want to make, because sometimes when we omit things, it turns out that we start getting ourselves confused, because it's like, oh, what's really going on here? Is this a two-dimensional entity, or is it really a three-dimensional entity that appears to be a two-dimensional entity? Because it isn't something that it has components along all three unit vectors. So with that, I will say that all components and again, this is not just exclusive to this idea of the cross product. Clearly, this could also, we could also run into this issue with dot products. So, and vector addition, etc. So please be sure we understand what's really happening with these vectors. And here I'll just note 0 or otherwise. So we just need to make sure we capture all of the components. It's pretty simple if they have some non-zero value associated with them, but we still have to capture it if that component has a 0 value associated with it as well. Again, as I already indicated, as can clearly be seen, the result of the operation is another vector. And an important property, and one that you can see if you actually reverse V2 in the table that I'm showing at the top of the screen right now, and V1 and the associated components, it turns out that V1 got my cross product in there before my subscript. V1 crossed into V2 is equal to the negative of V2 crossed into V1. It is not equal to V2 crossed into V1. Okay, so here we can't just reverse the order and hope to get the same result. That is not going to happen. So let's go ahead and look at an example. Let's say that we have V1 crossed into V2, and in the three space inspiration for this discussion, let's have V1 be 1, 2, 3, and let's have V2 be, and I am sure you will all be shocked, 4, 5, and 6. So when we look at the cross product itself, another way that we can, and I know we haven't introduced it yet, but another way that we can look at the cross product is as the determinant of a particular matrix. And I shouldn't say we can look at it as the determinant, but we can use the same pattern. That would be a better way to say it. We can use the same pattern as is associated with the determinant of a matrix, where the first row of that matrix would be the unit vectors, and the second two rows would be the components of the vectors, of course, in the appropriate order for the cross product. So if you saw what I was doing up here with the cross product and you said, hey, that looked a lot like what we, the pattern that we had for determinant. Yep, absolutely correct. And so as you know, with the determinant, or as you may have come across, with the determinant, just like I did up above, you reproduce the first two columns. And then we go ahead and start drawing our lines. Oh, and by the way, I do want to represent that this is equal to, before I leave this entirely, this is of course equal to V3. Okay, now we can go ahead. And put together, oops, missed my 6 there a little bit, and put together that pattern. Let's go ahead. I want to have that be a little cleaner. There we go. And of course, the minus, 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 that irritates me. There we go. Fantastic. And so in this particular case, and for no other reason than I used green before, let's go ahead and use green again. So for this first term, I have, sometimes I like to work up backwards. So I have 4 times 2 is 8 times k hat, and I get a negative. So I get a negative 8 k hat. Then I have 5 times 3 times I hat, negative. So I get a negative 15 I hat, and I get a 6 times 1 times j hat, and of course negative. So I get a negative 6 j hat. And then on the positive branches, I have 6 times 2 is 12 times I hat, so plus 12 I hat. 4 times 3 times j hat, that looks like another plus 12, this time plus 12 j hat. And then 5 times 1 times k hat, that's on the positive branch, so positive 5 k hat. So I can see then pretty quickly that V3, oh, and before I leave it all, leave it entirely, of course, this is equal to V3. And so then going back to my default color, V3 is equal to, so I have a negative 15 I hat, a plus 12 I hat. So it looks like I get a negative 3 I hat, negative 6 j hat plus 12 j hat looks like a plus 6 j hat. And then last but not least, a negative 8 k hat and a plus 5 k hat looks like that's a negative 3 k hat. And that represents vector 1 crossed into vector 2. There we go. Now, of course, if I reverse this, we wouldn't have to go through and recalculate all this. We would just know that we would have a positive 3 I hat minus 6 j hat and a positive 3 k hat, because, of course, the sense of the vector is simply reversed when we reverse the order associated with the cross product itself. So now let's go ahead and look at the interpretation of the cross product. So just like we looked at the interpretation of the dot product, we now have the interpretation of the cross product. So just as we saw with the dot product, the two vectors upon which the operation is being performed oops, my E got a little fussy there. will again create a plane. So that, of course, is no surprise. It turns out, though, that the vector resulting from the operation will, and here we'll have a colon because we'll have a couple things going on here, or several things, I should say. Will one be, let's go ahead and, I have them all just in one big paragraph, but that's a little obnoxious. Will one be perpendicular to this plane and after spelling out perpendicular once, we'll go and use the perpendicular symbol. So perpendicular to both. By necessity, that means it would be perpendicular to both of the initial vectors. 2, it will have a sense determined by the right-hand rule. No, don't ask me where that O came from. And of course, for us, right-hand rule will just be RHR. And these are all ands, all anded together. And 3 will have a magnitude of magnitude V1 crossed into V2 is equal to V1 times V2 times sine theta, where V1, V2, and theta are defined the same. Technically, I should say in the same way as, but that's okay. We'll just do the same as the dot product. So that gives us a bit of an understanding of what's going on with this particular idea of a cross product. An additional property, and I'll just go ahead and add it on even though I don't have it in my notes, but it certainly is important enough to write down. And the magnitude here, I'll just say that magnitude represents or can be interpreted as represent representing, but here I'll just say represents the area of the parallelogram I think it's a O. So check my spelling on that. Parallelogram created by the two vectors when they are used as the sides of that parallelogram. So we can see that these operations, all of them, but probably more specifically the dot product and the cross product, have a very rich or have a lot of connections and have a very rich set of interpretations. So that makes these two particular mathematical operations very, very interesting in and of themselves. But with that, I would like to just say that, of course, these and other operations, and of course, we'll discuss some more of those in the second part of our linear algebra review. These and other operations have been defined for matrices and vectors. And of course, they will be useful as we continue throughout this class. Here, I'll just say as we continue to study state space methods and, of course, linear algebra, which provides us the mathematical underpinnings associated with that particular type of representation. So we will be seeing more of linear algebra again once we get through our system descriptions using state space methods. But for right now, what we have covered will take us reasonably well through this idea of developing state space models for dynamic systems. So with that, we'll call this first part of our linear algebra review a wrap.